Okay, so this is what Mindu shared with me last time. So this is her code for the first question. So that is to write a function which give us n-1 terms starting from x0, where the first two terms are these, and from the third term onwards up to n-first term, you have to go with this. So this is basically Mindu's code, and just let me run this and show you. So when we were testing this code, when we give n is equals to 4, we got this answer. So for the first term it's 1, second term it's 2, third term it's 3. That's okay. For 5, yes, we are getting some answers. But when we give this one, that is test loop 3, it gives something really odd, right? Because we know the second term is fixed, it's anyway 2. So why are we getting 3? That was the issue. So that is happening just because of this for loop. It's going in reverse order, because when n is equals to 3, it starts by substituting value 3 here. So 3 minus 1 is 2. The for loop is looping from 3 to 2. So it's going in reverse order. So when j is equal to 3, it gets in the for loop and it works by substituting the value 3 to j. And when it goes back, j becomes 2, because you know, even if we give a vector, it could give in a reverse order, right? So if we give 1 to 3, it gives us 1 to 3. If we give 3 to 1, what happens? It gives us 3 to 1. So in R, it really works in the reverse order. So I'll explain you how this is happening. So whenever you come up with a thing like this is how I found, okay? This is how I found the error. I try to manually substitute values to this and see what's going on. That is how I also found that the for loop is going in the reverse order. So whenever you come up with an error, that is how you should try to fix it yourself. Learning that is also very important, because we won't be getting the perfect code at once. Any expert, we might have to do some trial and error. So the time really depends on how you how much of experience that you have, right? So let me snip this out and paste it. Think I can doodle on it when I save it as a PDF. Export. Okay, so I'm going to doodle on this. Thank you, Mindu, for sending me the code, so that everybody, including me, could learn something new out of yours. Okay, so in here, when we say n is equal to 3, right? So that is test loop 3. When we run this particular line, okay, we are get what do we get? 1, 3, 3. So this is something unexpected. Okay, so what I'm going to do here is, okay, so this says x1 is equal to 1 and x2 is equal to 2. right? So when you go inside this loop, we start from, so this is the loop part, okay, for loop part, right? When j is equal to 3, it goes here, j3. I'm just substituting values to this particular line, okay? So that is equal to j3 minus 1 is x2 plus 2 over x2. So here the value of x2 is 2, right? So that is 2 plus 2 over 2, which will give you 3. So the value of x3 is 3, right? So this is the first iteration of the for loop, right? Then it comes, so this is happening, okay? This is anyway happened because it's there, right? So this should be 2, but it gives you out 3. Let's think why, okay? So it goes in the second iteration. In the second iteration, j is equal to 2 because 3, 2, 1, likewise it's going, okay? So when j is equal to 2, we are getting x2, right? Is equals to, so when this is 2 minus 1, that is x1 plus 2 over x1. I just substitute the iterated value in this line. So what is x1? It's 1. Can you see how we get this value? 3. So here, after this iteration, the value of x2 is 3. That is why it outputs, right? So in the next iteration, what is, how is it going? Does it iterate any longer? No, right? So it can't go for x0, okay? So it can't go in thereafter, so it stops there and it returns the value of x. So x is what? x1, x2, x3, right? So x1, they print 1. So let me write it like this. What is x2? Is it 2 or 3? Because this is written, this is R, it is high level language, and also it compiles line by line. It doesn't read the entire code and output the answer. It compiles line by line. That is a feature in this programming language. So it compiles this line, it compiles this line, and thereafter this line likewise. Okay? So when it comes here, what is the new value of x2? Earlier x2 was 2. After this one, this 2 is replaced by 3. So after this line, what it outputs is the updated value. Okay, so that is 3, this one. Then it gives you the value of x3. This one. So this is the vector x. The values get updated. That is why we got something unacceptable as our second value. So this was the mechanism of this for loop. So the fixed code is uploaded in the LMS. Hope you all could go through it. Go through that. If you have any questions in that, just ask me. I have handled for the errors because it's not always giving outputs for any value of n. So if we give n is equal to 1, it doesn't output anything because it outputs n minus 1 terms. So it doesn't output anything, it just pops out an error. So you can do some error handling. So I have addressed all those in my code, just go through that. So there I have handled for this case as well. And when n is equal to 1, what to do, when n is equal to 2, what to do, else what to do. Okay, so I have used those statements to get the perfect code out of it, right? So you would be coming across these things only when you test for several cases. If you didn't test your code for several fair cases, you wouldn't be getting things like this. You might think, okay, I got one answer, this code is correct. That happens. We always cannot go for all the possible cases, so that comes out with practice. So always when you write a code, test for several cases, just like Mindu did, so that she could identify, okay, this was not working. So if you found out this was not working, you the next step is just write things up manually and see what's going on, what has happened, to get an output like this. And then you can change your code accordingly. So nice job done. So we learned something new. For loops can go in reverse order. Okay, so updating values is something like this. So let's say x, so this is something else, but just to tell you, I'll write it in somewhere here. Let's say some value f. We substitute 3. When we print f, it gives us the value 3. For the same thing, okay, I can give another value. So this is what you call overwriting or updating. Okay, when I run this line, f is no longer 3. When you run this line, see, it is 4. So something like that had happened in this code. x2 was initially 2, but after running this code, the value of x2 was updated with 3. So that is why at the end, when it outputs values, it doesn't give the initial value, it gives the updated value when you run this line. That happens only when n is equal to 3. You can manually write things and see what was going on, why it's not happening to n is equal to 4. So you all can individually study this just by what is that? Doing, just scribbling out things like this. I hope this is understandable. Any question here? Is this clear?
Yes, ma'am.
Okay, good. So Mindu, you can now understand, and everybody could understand what had happened. So yeah, right. You can take, you don't need to, but if you want to, you can take a screenshot of this. I'm not going to upload this, but you all can simply handle this. Okay. So today's lecture would be depending on the infants data set. Once again, I just put a notice in the LMS. I don't know whether you could go through that. So for today's lecture, we would be needing this one. So you have this data set already saved in your machines. If you can't find it, just download it here from lecture 3. So today we are going to learn hypothesis testing. You all have already known that, but we are going to see how we're going to do that using R. Okay, so this is basically what why we are doing computational statistics is because you know, yeah. I'll just take a new script so it's easier for you to understand. Just be ready with the infants data set. I have my code typed here, but when teaching, I think it's better going in a clear script so that you all can understand the steps. So today we are going to do hypothesis testing. Yeah, so first of all, I'm going to take a new script and import the data set. So it is a txt file. So I'm going to check whether all these things are okay. So this is the data frame. This is how it looks. It has its own column heading. So I'll just keep heading is equals to yes. I can just keep this if we want to strings as factors, so that we don't have to coerce them into factors. They take it as factors, these string values. You can either do it later on if you want to, or else initially you can tick that out and click on import. That's the easiest way of doing that. Just to keep my script complete, I am okay, let me redo that. Something wrong. Okay, name is infants. I think I have typed something here. You can always change the name of the data frame here. Okay. Right. Oh. Okay, I'm not happy with, I don't know what's happening here. Some malfunctioning in this PC. It's easier for me to like this. Okay, so after that, I am going to view what my data set is, just to see whether, yeah, it gives the proper thing. These are the variables that we have in the infants data set. So yeah, just for the ease of access, I'm going to attach this file so that whenever I'm calling out the variable names, I can call them directly rather than using the $sign after this. Okay, so without attaching, if I I already compiled this code, so it has already been attached. So if not, if you're using the, okay, yeah, it's already been attached. So okay, then I'm going to attach this file just for my, it's already been attached in my computer, but when you're starting an initial thing, you don't have to, but just to make it easy, see, it is masked from infants because it was attached initially, right? So you won't be getting this if you're doing this initially. You're going to attach this, right? So I'm going to perform hypothesis testing. So we know we'll start with just one sample test. When you have a particular sample, you are going to check whether a mean or some statistic. Let's take the mean. That is the usual thing that we come after. The mean of something is happening with my computer. Okay. The mean of something is equal to some hypothesized value. It's greater than or equal to some value. It's less than or equal to some value. So we'll check H0, H1, which you learned in mathematical statistics second course in the last year. You know how to perform hypothesis tests. So we are going to learn how to do it using R, so that you don't have to compute things manually. You don't have to check statistical tables. You don't have to compute the test statistics. It's just depending on the p-value, right? The probability value, and you're comparing that with some significance level or the confidence level, and you're giving all the results. So it's very easy to do it using R. You're saving a lot of time when you use statistical software to do that. Does anyone know how to sort this out? This is automatically giving us some. The screen gets zoomed out all the time. Does anybody know how to sort this out? This equal sign is automatically typed. I don't know what's happening. Fine. Let's manage. So I'm going to deal with this particular column, age. Okay. I want to see whether the average age is different from some value. So for that, I can either perform parametric tests, or I can either perform non-parametric tests. So the thing that is required from your end is to be thorough with all the rules. You all know that we cannot go for one sample t-test all the time unless otherwise it satisfies certain conditions, right? The data set should not be normally distributed. If not, at least the sample size should be very large enough. So things like that has to be considered. Let me close this and get that. This is annoying. Where will it be? It's not needed. Okay. Right. So just because I want to test, let's say I want to test whether the age, the mean age, average age of basically mothers of the infants, right, is whether it is 25. It's different from 25. So what would be our H0? So basically our H0 is what? Age is equal to whatever the hypothesized value you are interested about, right? So if you are supposed to test this, you first have to decide whether you are going to perform. So this is basically one sample test. This is a quantitative variable, a continuous scale variable, right? So for that, you should first check whether it's possible for you all to go with a parametric test, or else you have to go for a non-parametric test. So the first thing that we are doing is checking whether this is normally distributed. So there is a certain steps. You anyway can go for a normality test, but there is a couple of things you can do instead. First, you can see the distribution. So let's just draw a histogram. How do you draw that? Hist, you give the variable. So by eyeballing, you call it eyeballing, you can see it is slightly a skewed distribution, but just because you have a very little observation, very close to zero observations here, it is approximately normal. But just by looking at a histogram, you really cannot exactly say things. This is drawn for the sample. So by looking at this, you anyway cannot say this is normal. You have to anyway go for a hypothesis test. Right. Here, by drawing the distribution, the condition that we are checking is not that whether the data are symmetrically distributed. That is something else. True that normal distribution is a symmetric distribution, but just by looking at the histogram, you cannot say, although it showed you a bell-shaped symmetric curve, you can't say, okay, we can put t-test for this. No. Why? Because every symmetric distribution is not normal. For example, t distribution. It is a symmetric distribution and it's symmetric around 0, but it is not normal distribution. So the condition here is data should be normally distributed if you want to do perform a t-test. At least the sample size should be large enough. So by central limit theorem, the limit in distribution converges to normality. So you all have learned these things last year, just recall. So just to see things, we just as a descriptive analysis, we just looked at the histogram. We anyway saw that this is not normal, but this is the sample. We don't know in population whether the age is normal or not. So what are we doing hypothesis test for? We are checking whether, based on sample data, we are checking whether the population behaves like this, right? That is why we do a hypothesis test. We always make inferences about the population based on the sample data. So whatever the conditions that we get from the hypothesis test is generalized for the entire population, not for the sample. So what is the mean here? Is this a sample mean? Can anybody answer? What mean is here? Can you, let's say mu is equal to 25. So what is mu? Mean age. What mean? Population mean or sample mean? Can somebody answer? It's okay to go wrong, just give a try. In hypothesis testing, what do we put here? Population or sample measure?
Population.
Exactly. Thank you for answering. It's population. So if we write mu here, mu is equal to 25 versus h1, mu is not equal to 25. If we check that hypothesis, how do we define it? Let mu be the population mean age of the mothers of the infants, something like that. We always define the parameter. We write the parameter here. We are checking whether the population mean age is different from this value. That is our hypothesis here. Okay, based on sample data. If we take the sample mean, it gives us 24.75. This is not the population mean age of all the mothers of the infants. This is for this particular sample, right? So we are making inferences for the population. So I just wrote mean age is equal to 25. This is what I'm interested to check here. So in R, the normality test, the function in R is Shapiro. We perform Shapiro test to check the normality. So when checking the normality, what is H naught? Data are normally distributed. Basically, this is H naught. H1 is data are not normally distributed, right? In normality test. Okay, so in R, how do we perform normality test? Shapiro dot test. That is there in basic R package. So without any additional package, you can use this. So here it's just a matter of giving the variable you are going to check. So we are going to test whether the age is normally distributed or not. It gives out the results. So how do you read this? Shapiro-Wilk normality test. So this is the name of the test. Data, they're referring to the age of this one. Okay, and this is a test statistic. We don't know how it is computed, but in the normal test, a test statistic is computed. But we don't have to worry anything about that. We are given a p-value. Okay, we are given a p-value. So what is the decision rule based on the p-value in any hypothesis test? Reject H naught if p-value is less than a significance value, that is alpha. We are doing the test for a certain confidence level or a significance level. 95% confidence means what? 5% significance. Right? You can tell it in either way. Right? So let's say you're checking this for 5% significance level. So what is your alpha? 0.05. It doesn't have to be that all the time, but we normally using that one unless otherwise specified. If I ask you to perform a statistical test for 1% significance level, you have to compare the p-value, whatever the p-value you're getting, with 0.01. If I tell you to do it for 10% significance level, you are comparing this p-value with 0.1. So likewise. So we'll go in the basic terms here. We are, this is whatever the confidence level that we are handling, this is the p-value they are giving. So we are supposed to compare the p-value with the confidence level that we are interested in. So here, if we go for 5% significance level, we are checking whether the p-value is less than that. What is the decision rule? Decision rule is reject H naught if p-value is less than alpha. So I'll just write significance level. If we go with the test statistic, right, we don't know the decision rule, right, because we don't know how this Shapiro-Wilk normality test is constructed. We have to survey on that. We have to research on that. We can, right, we have to do a little bit of survey. Whenever a p-value is given, you always have to go with this decision rule. Reject H naught if p-value is less than this one, right? So what is the p-value here? It's this, right? So the decision is what? What is the decision? P-value is equal to this, which is less than our significance level. So rule is what? Reject H naught if this happens. Hence, H naught is rejected with 5% level of significance. So when you are doing a hypothesis test, I hope you all know you have to write H0, H1. Just because I didn't write H1 doesn't mean that you don't have to write H1. I'm just commenting out things here. So if you are asked to perform a hypothesis test in your answer script, you have to write H0, H1, and anyway, this is R, so you don't have to compute anything. Just run this code line, and you have to mention the decision rule, reject H0 if p-value is. So you don't have to write this one. Besides this, you can substitute your significance level, which is given in the paper. I would say check the hypothesis for 5% significance. So you can simply write reject H0 if p-value is less than 0.05. You can write that. Okay, just be careful about the significance level that I give you. Okay, so what if I ask you to check this hypothesis to 1% significance level? You are checking whether the p-value is less than, sorry, yeah, you are checking whether the p-value is less than 0.01. In that case, what happens? Is this value less than 0.01? No, it's greater than, so you accept H0. In that significance level, you say, okay, this data is normally distributed, and you can simply perform the t-test, right? Just because I'm checking this with 5% significance level, p-value is static for anything, right? P-value is static. We are checking this with our level of significance. So according to my interest, I cannot say that data are normally distributed because H0 is rejected with this percent of significance level. You have to write this whole statement completely. You always, when you are writing the decision, you have to say whether H0 is rejected or not, and you must give the level of significance to make it complete, otherwise you lose marks. You have learned these things previously, and then you write the conclusion. So you all have learned when you are writing conclusions, how do you do that? You always go in the plain language, right? So basically here, data are not normally distributed. This is your conclusion, right? So you can change this value if you want to perform a t-test. If you want to go for a parametric test, you can decide on this. That's fine, but we should learn both things, right? Actually here, although this Shapiro test gave us that age is not normally distributed and the histogram seemed to be a little bit skewed, you anyway can check whether the sample size is large. How do we check that? We just get the length. Okay, so the length of that particular variable is at 68. Usually, this is what people have found. Don't ask me why we say that this is a large sample. This is the general case. Researcher can really decide whether this is large enough or not according to the problem context. These are highly applicable things. So it all depends on the researcher. Usually, we say it is a large sample generally if the sample size is greater than 30. People can say if it is greater than 40, we consider it to be a large sample, right? People can say if it is greater than 100, we say it's a large. It really depends on the problem context. For example, let's say you are doing some research on employability of differently able people, disabled people. So it's highly unlikely to find an employed disabled person. Let's say a person without a leg and a hand, let's say, it's highly unlikely to find some employing person, right? So in that sort of a problem, if you are doing a sample analysis, it's practically not that easy to find a large data set. In that case, you cannot really restrict your study. Okay, to make it a large sample, I have to collect more than 30 data points. You cannot go with this role in that case. But let's say you're trying to find some probability, or let's say in the next election, who would be the winning party. So for that, you can do sample election surveys. You might have already gone into those things in Facebook or any other social media. People do polls, right? So it could be done officially or not unofficially. But for that sort of a thing, you cannot say if the sample size is greater than 30, it's large enough. No, because polling is, we always collect population data when it comes to the final real decision, right? We consider everybody's vote. We don't consider only a sample, right? We don't say, okay, Colombo people, Gampa people, Kandy people can vote, and that is going to be the final decision of, let's say, the presidential election. So you are not saying that, right? You consider the votes of all the people, all the 18 plus people in the country. So that is your population. So for an experiment like that, you cannot say 30 is large enough, right? So it really depends on the situation, but generally, the general cases, researchers, literature, when you review literature, you can find this fact. We consider a sample to be large enough if it is greater than 30. So here, if you like to, you can say this is a large sample. It really depends. You can say this is not enough, right? I'll tell you exactly what to do at the exam, because at the exam you can't do different things. So in practice, this is how we do. This is a large sample. So by central limit theorem, you think that the limiting distribution is going to be normal. So you apply a parametric test, assuming that the data are normally distributed. Although this thing gives you data not normally distributed, although the histogram shows you it is skewed, by reasoning out, you can say, I'm going to do a parametric test just because it is a large sample case. Acceptable. Okay, in practice, it's acceptable. If you're doing research, you can say this. At the exam, I'll tell you what to do. Just because all your answers should be the same, almost the same. When I'm giving a question for hypothesis testing or whatever it is, I would make it clear. If I say, consider this as a large sample, just don't check the sample size and all that. You don't have to. You can approximate normality, but you have to mention. Just because the question says it's a large sample, I'm approximating normality to this data set. You have to say that, because I have to know why you performed a parametric test when the non-parametric tests are available. We always try to go for a parametric test. Why? Because the power is really high. Power of the parametric test, the result is very high compared to a non-parametric test. We in statistics, we always first try to go for a parametric test. Only if we cannot do anything, we are going for a non-parametric test. We try to give reasons, give adjustments, make adjustments, and we always try to go for a parametric test. At the exam, if I say it is a large sample, you can consider normality. You can consider, okay, this is a large sample, I approximate normality, but you have to say that, right? If I didn't say anything, You can't go for large sample approximation, although the sample size is 500, right? At the exam, you have to perform a hypothesis test in the given significance level and test whether this is normal or not. I will give you the significance level. Even this you can't rely on. Okay. If I didn't give the sample size is large, you have to perform this one in this sort of a case. And if the data are not normally distributed according to the significance level that I give, you have to go for a non-parametric test and you have to reason that out. You have to say, okay, I did this one, I did Shapiro test, it gave out that the data are not normally distributed, so I went to the non-parametric test. You have to reason out everything clearly. If I say sample size is large, don't even think about the length of the sample. Just go for the parametric test. That is how you decide at the exam to which test you should be good. I won't say do a parametric test, do a non-parametric. I won't say that, but I will give you tips clearly. I'll make the question clear enough so that you can decide. Okay, so that is how the exam is done. Right. So just because I want to teach you both the parametric and non-parametric test, I'm doing both the things here. Okay, so basically I'm going to perform, so I'm going to say the sample size is large, so I'm going to use the parametric test. Don't take that thing serious. Or even I could say something like this. I can change the significance level like 0.01, right? I can increase the confidence, 99% confidence, and say H0 is not rejected. We do not have enough evidence to reject H0 with 1% level of significance, and I can simply say data are normally distributed. Anything, right? Usually, if the data are normal and if all the assumptions are made, usually we don't go for non-parametric tests because parametric tests, in a place where we can perform a parametric test, we are not bothered about non-parametrics because the result power is very low. Okay, so we'll see how the parametric test is done. Okay, so this is basically the one sample t-test. I assume normality here. My argument is this, or even I can change the significance level and say it's normally distributed, anything. So the test is, this is the code. T.test. Basically, this is for the t-test. And there, after this thing appears here in R, just press Control and space bar. Control key and the space bar key, you are getting all these things, right? So X is basically the data. Just because this is one sample test, you don't have two samples, so you are not giving this Y, right? Mu is the mean. Basically, mean means the hypothesized value here. Hypothesized value here. So that we are checking it with 25. We have to tell R whether this is a two-sided test or a one-sided test. What does it mean? Two-sided means something is equal to something versus something is not equal to something. One-sided means what? You put greater than or equal mark here, less than mark in H1. Or you put less than or equal mark here, one-sided. You are checking whether it's less or greater, right? And less than mark in H1, likewise. So how do you give that in R? You just say alternative. Here, it gives you the help. The character string specifying the alternative hypothesis must be one of these. So by default, it says two-sided. So if you want to perform a two-sided test, you really don't have to give this argument. Why? Because by default, it performs a two-sided test. Okay, by default, that is it. So just for knowledge, I'm just writing that out here. Or if it is one-sided, you have to put greater or less. So I am checking whether the mean is different from 25. So my alternative is what? Within inverted commas, I have to give two-sided. Here you can either confidence level, I really don't think so. You have to do, let's see. Okay. You can either give the confidence level or not. If it is different from 95%, you can give. So I'll just put this here. These are optional. It's because this output really gives the test statistic value, degrees of freedom, p-value, right? And it specifies the alternative hypothesis. See, true mean, that means the population mean, is not equal to 25. So that is our H1. Just because we give 95% here, it gives the confidence interval for mean age. This is the lower limit. This is the upper limit. So these are additional information, right? Of this test. So if I ask you to do it for 90%, it gives the confidence interval for 90%, right? See, if you didn't give anything, by default, it gives you the confidence interval for 95%, right? So just to practice these things, you always give all these arguments, right? Even without giving this, you can get the p-value. So just because we are doing a test here, we are interested only about the p-value because we are doing a hypothesis test. We are going to check this, compare this p-value with our significance level, right? And it gives the mean of x also. What we got here, right? So this is basically the output. So by giving this output, you could be asked different questions at the exam, right? Perform a hypothesis test. What is the confidence interval for this? So you don't know to get the confidence interval by running R code, but you should remember when you test this hypothesis, you're automatically getting the confidence interval, right? So questions might be test the thing, whatever the thing, for 95% confidence. Then you would be asked obtain 99% confidence interval. So how do you do that? You just run this code line with 99.99 here and just extract the information that you want. And this is given only for two-sided case. If you give greater or less, it doesn't give you anything. Okay, so we perform the t-test and simply we have to write all these things here. Okay, so what is the decision rule? Reject epsilon if p-value is less than significant level. So here you can put the significant level, right? And what is the p-value? It's this. So is it less than? No. Hence, it's not is not rejected. Okay. So what is the conclusion? You always go with plain English language. It's what is it's not here? What did we test here? We tested this one. Okay, so this is our it's not. It's not is not rejected. We do not have enough evidence to reject it's not. So conclusion is what? This one. That's how you write the conclusion. Okay. So if somebody decided, okay, this is not normal distributed, I want to go for a non-parametric test. How do you do that? So this is go to the non-parametric test. So same hypothesis I'm checking. The code is this Wilcoxon text, right? It's also in the base package, so you don't have to install any package. So when you press Control spacebar, you're getting the drop down. You have to give the same arguments here. Yeah, also you have to give the hypothesized value, alternative, everything. You can even simply copy and paste this thing. Just copy and paste this thing. It's enough. This is two-sided because we have the equal sign here. What are we getting here? Wilcoxon sign rank test with continuity correction. So this is basically the non-parametric test that you're using. And this is the p-value. So this is greater than 0.05. Hence, we do not reject. Okay. So this is basically the conclusion. Here you can write 0.05. Here also you can write. This is the general thing, so I write. At the exam, you have to write the value. This is the general decision rule for anything. It can be 1%, 10%, 25%, anything. Okay. So just because this is not really a serious case from the parametric and non-parametric, both the tests, we have gotten the same conclusion. Mean age is 25 years, right? You can do the same thing for different confidence levels. You can do things like this. At the exam, you have to write H1 as well. You don't have to comment anything, but at the in the answer script, you have to write in relevant places. I'm just commenting for you to show how you should word this, okay? By using symbols or anything. You don't have to comment. It's okay if you comment it or not in the R script, but in the answer script, you have to write the entire thing. So let's say we're checking this one. And you are going to perform a non-parametric test. You can do parametric and non-parametric, anything. I'm just showing you the code. So if this is the case, the alternative is why? Why is that? Because H0 is greater than or equal, right? So what is H1 then? Alternative is what? H1, right? Don't confuse. Just because this is the greater than sign, don't write greater here. Then it is completely wrong. Always what we give as a parameter, what we give as an argument here is the alternative hypothesis. So if you write H1, what is it? What does it? How does it construct? So this is the less than mark. This inequality is the less than mark. So that is how you give. If you are asked to check this hypothesis, remember, you have to specify the alternative like this. So this is the result. I'll just write it for your knowledge. So this is the decision rule. Our key value is this one. So yeah, it is greater than this value. So it's not rejected with this percent of level of significance. That means it's not is correct. You can say mean age is, you can either say mean age is greater than or equal to 25, but to make it sensible and to make it naturally speaking English language, you can say mean age is not less than 25 years. Yeah, so you can say not less than, this is less than, so it's not is accepted, so you can say it's not less than 25 years. If it's confusing, you can say mean age is greater than or equal to 25%, but you can't write mean age, you can't copy and paste this one here. It's wrong, because the conclusion should be always given in plain language where a non-mathematician or a non-statistician can understand. So you can't use mathematical symbols, mathematical terms here in the conclusion or the interpretation. You always have to keep it in plain language. So you have, if you are writing greater than or equal to, instead of this, if you're writing greater than or equal to, you have to write it in letters, English letters, greater than or equal to. So it's time saving to write it like this. Okay. So just because you have the data set with you, I want you all to try all these things. I'll give you like 10 minutes because we are going to handle the 2 sample case as well today. Yes. Yeah, I'll give you just 10 minutes, but not more than that. If you have questions, please ask. Just get the data set and I hope you can see the screen. Just practice, I'll give you 10 minutes. If you have questions, you can ask in interpreting or in understanding these things. If you have any question, you can ask now while practicing this. Just use 10 minutes. Okay. Right, I'll be giving you the our script, so don't worry. So let's try a 2 sample case. So if y'all remember, when you have to do the 2 sample case, through that you have to check whether the 2 samples, 2 independent sample case we are doing now, right? Whether the 2 samples are normally distributed, you have to check that. And also you have to check whether the variances are equal. So that for that you cannot go for like check the sample variances of both the samples and say whether it's equal or not. That is not the case. Just like the normality test, you have to do the equal variance test, right? So let's learn that one. So basically, anyway, we have to design our 2 independent samples. So I'll go with this code. Yeah. So how am I going to split the code is by, let's say, I'm again comparing ages. So when we take this particular variable, we have the infants who were breastfed and who were not breastfed, right? So I'm going to split this particular data set by this particular variable, and check whether the average age of the mothers of the infants who were breastfed is different from the average age of the mother of the infants who were not breastfed. Makes sense, right? So for that, I have to have two independent data sets. So by this thing, I am going to split the variable, this one by this. So how am I going to do that? Let's just copy paste. So age years means age of the mothers of infants who were breastfed. And age no means age we select, this is the command, okay? Age we select breastfeed equals yes. Age we select breastfeed equals no. That means we select the ages that the breastfeed is equal to no, this one, this one, this one, this one, this, these things. Likewise, we are going to split the ages according to the fact that whether the infants are breastfed or not. Okay, that is what I have done here. So if I run this thing, I'm getting the ages of all the mothers who their infants are breastfed. 26, 35, 22, 23. So let's go to our data set. 26, 35, then 22, right? Next one is 23. So likewise up to the end. End is 20. This one. So if I print this, I'm getting all the ages of the mothers who their infants are not breastfed. Okay. And then I can simply check the sizes of the sample, just in case if we had to approximate normality. So that is basically length of this one, length of this one. And I got these answers, 36 and 32. Right. I just copy and paste this code. It's easy for me, time saving. It gives 36. There are 36 observations in the sample where the infants are breastfed, right? And if we run this, I'm getting 32. So I have commented these things here. Since both samples are more than 30, one can approximate normality. So this is just one way. But at the exam, I told you, if I tell you this is large sample, you can approximate this one. Otherwise, you have to do the Shapiro test, the normality test. So how do you do the Shapiro test? Right, like that. So here you just check the p-value with 5% level of significance. So this is less than 5%, 0.05. So we reject H0. That means the data, this data are not normally distributed. Similarly, we can do this for this one. Again, the p-value is less than 0.05. So we reject H0. What is H0? Data are normally distributed. We reject H0 means what? Data are not normally distributed, right? By Shapiro test, we are getting that the data are not normally distributed. Not only this, anyway, we anyway have to go for Shapiro test to check it perfectly with the high p-value. But there's another way. You should not be familiar with this QQ plot, quantile plot. So in this week's regression lecture, hopefully you would be able to learn that. QQ plot, what does that mean? So in R, you can get that, okay, by these two. Okay, QQ norm means quantile norm, right? When you so this is a code to plot the quantile plot. So here in the y-axis you are getting sample quantiles. Here you are getting theoretical quantiles. You will learn this in the regression lecture this week, hopefully. So don't worry too much about it. The requirement here is this should possess a diagonal line. A diagonal line. So here seemingly it is, but by running this code, you can simply add the line, right? QQ line. So this is the QQ line. This is not going in this line, right? So actually these data points should go in this line. It's not perfectly going to be on that line, but somewhere like this. So these observations also should come here. It's going beyond the line, means it's getting skewed. The distribution is getting skewed. Okay. Similarly, you can draw a histogram for each years. And see it's getting skewed when it goes to the top observations. This is called positively skewed, right? Same thing you can do for age no. Don't worry if I erase these things and do, because I'm going to anyway upload this particular script to you. So I'm going to get the QQ plot for age no variable and then the QQ line. Here also I can see some deviation. Anyway, the Shapiro test gave that this is not normally distributed. This has to go in line here. So by looking at this plot, you really cannot like exactly say this is normal or not. This is just for the descriptive analysis. A couple of ways of doing the normality test. But exactly you can tell whether this is normally distributed or not by this one. Not by using the histogram, not by using the quantile plot, nothing. Just by doing the test. But usually in statistics, we go for descriptive analysis first and take some idea about the sample and then perform the hypothesis test and all that advanced analysis. That is the basic way. So if you want to do this in a report, and if you don't want to have these plots for the two samples independently, if you want to have these plots in the same panel, there is a way of doing that, right? So that is this code line. Pa means partition. Partition. You are going to partition this panel. MF row, C is just for the vector. This is the row indication. This is the column indication. So if I want something like this, if I want to have one row and two columns as the plots, I have to give 1, 2, just like the matrix indication. I want to partition this plotting area to one row and two columns just to have plots. So you are simply going to run this line. And you are going to run this one for the QQ plot of age years. See, can you see the part? This is partition for two columns, just one row, right? So here in the left side, you are getting the QQ plot for age years, right? And Okay. Can you see the next plot is coming there? You can partition it to 3 by 3, 10 by 10, anything, right? So let's say you partition this thing as 2, 1, that is 2 rows and 1 column. I don't know whether you're getting a nice plot there. I'm going to have 2 rows and 1 column. Let's see. Now I'm partitioning it like this. See, this is how the first plot appears, because I have to have 2 rows and this plot here. So this is, this is not looking nice. So it's always better to go like this. Even you can add another plot, or just say this is 3 by 3, you're getting 9 plots. 1, 2, 3, 4, 5, 6, 7, 8, 9, like that. 2 by 2 if you want to have 4 plots. Just have and see. So this is the first 2 plots. Again, let's say I'm plotting the same plots. You can have different plots, doesn't matter. Let's say I want to have the histograms. Anything, you can have anything. Just to make this sense, I'm going in this order. So histogram comes here. 1, 2, 3, 4. That's how it appears, right? So like that, you can partition it. And if you want to get it back, the next plot, if you want to have it just one plot in a single plane, what you have to do is run this code. Just copy this code and have it 1 row, 1 column. So that means just 1 plane. Right? Thereafter, if you draw a histogram or anything, you are getting it to the same plane. Right? Okay. So that is about partitioning. Not a big thing, but just in case if you had to write it. Okay. Then I can perform, I think we performed the Shapiro test. Yeah, we did the Shapiro test for age, yes and age, no. And we got the p-values which are less than 0.05. So both the samples are not normally distributed according to this test. Still, just because the sample size is large, this is greater than 30, this is greater than 30, one can think of performing 2 sample t-test, right? Same thing. Oh, wait. Before doing the 2 sample t-test, just because it is 2 sample, you have to check for equal variances, right? What is the test to check for equal variances? That is the Bartlett test. There you have to give these variables as a list. Okay, so you are going to check this one and this one, 2 independent samples, whether the population variance of this is equal to the population variance of this. That is what you are going to check by Bartlett test, right? So we would be needing this fact to perform the t-test. That's why I'm doing this initially. Just like we did the normality test, we have to perform this and check whether the variances are equal. If you refer the previous notes, you will get to know if you had learned this. If you had done, for example, t-test in your mathematical statistics course. If not, it's okay. For 2 sample t-test, you have to check for equal variances. It doesn't have to be equal. It doesn't have to be not equal, but you have to check and use the fact whether you're going to use this pooled variance or the same variance, right? That is why, because the variance term is coming in this test statistic when you're using the test. That is why you need to do this. So that is the Bartlett test, right? There you have to usually you give it as this. And when you do that test, you are getting a p-value. Which is greater than 0.05. So it's not is not rejected. What is it's not here? This is for equality of variance. What is it's not? Confusion is not. What variance is? Population variance, right? So always we are doing a hypothesis test for population parameter. So population variance of this one, population variance of this one, they are equal. Just check the sample standard deviation to the power 2, that is the variance. This is the sample standard deviation of age years, sample variance of age years. Just the sample. See, when you take the sample, they are different, right? This is 24, but this is 26 something. So by looking at these two, you can't say whether they are equal or not equal. That is not what we are checking. What we check is whether the population variances of these two are equal or not. That is why we perform a separate hypothesis test for that, right? So doing this is not relevant. Now we know the variances are equal according to this test, and now we can perform the t-test, two sample t-test, if we think that the data are normally distributed, or if we can say it is coming from a large sample, right? So that is basically the t-dot test, right? Control space x, you give the first variable. Why you give the second variable? Just because this is a two-sided case. Even switching these two is fine. I'll tell you why. Right? Everything else is the same like the previous case. When we run this, this is what we are interested about, right? P-value, this is greater than 0.05. So we do not have enough evidence to reject H naught. What is our H naught? Whether the ages of mothers of the infants who are breastfed and who are not breastfed, mean ages are equal. That is our H naught. So our conclusion is yes, they are equal. I'm not writing the decision rule and all that here, right? But at the exam, you have to write. Mean ages are equal. That means age years is equal to age no. This is the conclusion by the t-test, right? Similarly, we can do the same thing as a non-parametric test, right? It's the same code that you have to use wheelcock.test. I'll just copy and paste from this one. Sorry, I have to give this one as well. Sorry, for this one. This argument means variance dot equal is true means equal variances. Actually, we got this for equal variance case because by default, this test give you variance dot equals is to true. So we're getting the same result, same p-value, right, as the earlier case, because by default, sorry, we didn't get it. By default, it gives variance dot equal is false, right? That's why we got different p-values here. This one, this is different from this. So if you give false here, see, you're getting the first p-value. That means by default, two sample t-test assumes that the variances are not equal. What we tested here, okay, but here we got the result that equal, the variances are equal, so you have to mention that this is true, otherwise you are getting a different p-value. But anyway, the conclusion is the same. Both the p-values are greater than 0.05. But anyway, at the exam, if you didn't do this, you will lose a little bit of marks, because you have to mention this here. By default, it assumes that the variances are not equal, right? So you have to have this one as well. So if you want to do the non-parametric test, it's this one. Here also you're getting the confidence interval for 95% confidence level, just because we gave it, although we didn't give this, you are getting the confidence interval for 95% by default. If you change the confidence level, you are getting the same p-value anyway, but different confidence interval. Okay. So here, for this one, I'm not sure. For the non-parametric test, whether you're giving the equality or non-equality is not really, does not really matter, because this variance test is done only if you are doing the parametric test, right? For the non-parametric test, that is not needed. You simply can give this. You will be getting a warning message, just don't worry about that. Sometimes you will be getting, sometimes you won't be getting. That is because we have ties here. Ties means the same observation repeated a couple of times. So what it says is, in R, for two sample independent case, they usually do not adjust for ties. That's what they say. Manually, if we are doing this, we handle the tied observations, right, manually. The p-value would slightly be changed, right? But here what they say is, they don't have the facility to handle tied observations, right? If we didn't have tides, the same thing repeated, they would not give this message. Just because our data set have tied observation, they are giving the warning message. Just disregard that, get the p-value and make your conclusion. So here the p-value is less than 0.05. What does it mean? That is an interesting thing, right? So it violates with this one. P-value is less than this. So we reject H naught. What is H naught? Does it find it? Yeah. Here the p-value is greater than 0.05. We accept. Here the p-value is this one. Which is less than. So we reject H now. See, same data set, same hypothesis, different tests, different conclusions. Earlier case, in the one sample case, it was not too serious whether it's normal or not. That means it should be slightly not normal. That may be the reason. Even for the parametric test and the non-parametric test, we got the same result. This is the parametric test. This is the non-parametric test. We got the same conclusion, right? Earlier case. Here, we are getting different conclusions. Here, we accepted H naught in the parametric test. In the non-parametric test, we rejected H naught. Why? Why did we did the parametric test? By assuming the sample sizes are large. I told you it's greater than 30, so we assume normality. But that assumption is not really right? Because in the Shapiro test, it said it was not normal. Even by these, we saw that's not going in line with the QQ line, quantile line. Even in the histogram, we saw that it's not normal. So that means this is crucially not normal. Although we assume, see, this is 32, 36, slightly greater than 30. So that means in this case, they don't really consider these to be large samples. Or although these are large samples, the limiting distribution doesn't converge to normal. Right? So things like that happen. That's why I said, like the exam, don't do assumptions. If I don't give you that is a large sample, don't do assumptions. Your final conclusion might be changed. See, we need a parametric test, assuming that the data are normal, and also just to teach you how this should be done. The conclusion was the ages are equal. But here, the conclusion is ages are not equal. Right? Completely contradictory conclusions when we change it from parametric to non-parametric. So assume in the real case, if somebody performed the t-test and conclude that, okay, the mean ages are the same for those who breastfed their infants and those who are not. That is a wrong conclusion to the world, right? Because this test is not valid enough at this case. But a person who did a person who does a non-parametric test would say the mean ages are different, right? So selecting the test is very important. Selecting the correct test, the correct place is very important. True that we always try to go for the parametric test as much as possible, but that trying out means at the end you should be getting the correct conclusion. That's it, right? So here, going for a parametric test is not really a good idea, because in the non-parametric test we got. So it doesn't mean that this is 100% correct, right? We are 95% confident that this thing happens. Here also we say we are 95% confident, but just by common sense, we know we use the wrong test in the wrong place. But I just want to teach you the two sample t-test. That's why I had it here, just by saying I approximated large sample here. But actually it's not, right? So I hope there's no confusion for you all at the exam. If I give you assume large sample, that means you can assume the data set is normal. rather than doing a Shapiro test, that's fine. If I didn't give anything, you have to go in steps. You have to do the normality test. If it is not normal, you have to go for parametric test, and you have to reason out, this is the reason that you went for the parametric test. If I didn't give you the sample is large enough, and if you assume that the sample is large and go for a parametric test by mistake, then you would be losing marks. So don't do assumptions at the exam, but reason out whatever the step that you're taking. Okay, so what we learned today is to handle the hypothesis test parametric and non-parametric for one sample case and two sample independent case. So just because you have the data set with you and so many other variables, just like age, and so many other categorical variables, just like breastfeed, right? You have smoking variable, you have ethnic variable. I think for smoking you can, but for ethnic you cannot, because we have 3 categories here. You still can by choosing 2 of them, right? Try to practice the 2 sample test. Try to reason out. Just don't forget about this equal variance test when you are going for the 2 sample t-test. Don't forget it, because you have to give this argument. Sorry, you have to give this argument in the 2 sample t-test. If you didn't give, it assumes the variances are not equal and give you the p-value. So at the exam, if you didn't give this and got a wrong p-value, then you're in trouble, right? So always remember, you have to do this test. You're getting marks for this. If you don't do this, you're losing that particular marks, right? So when you're doing the t-test, if you want to get the correct p-value, you have to specifically mention this argument. Right, and this is the corresponding non-parametric test. You don't have to give this argument here. So I'll be posting this particular R script for you. So everything is there. I have not completely written the hypothesis test in any script, but you don't have to comment in the exam. You have to write, right? Just run the R code and write. You don't have to comment all these, but having comments would be beneficial for your reference, right? It will give you a nice code. It's easy for your reference. But at the exam, if you are asked to do a hypothesis test, make sure you write it's not and it's one. If you are using symbols, please define them. Like, for example, mu is the population mean age, something like that, right? And you have to mention the decision rule, have to mention the decision, keep the confusion in plain language. If you use technical terms here, then again it's wrong. Wrong means not acceptable. So be mindful on that for the exam. But as an R script, this is more than enough. You don't have to have any of these comments at the exam. I wrote this for your own comfort. So thank you very much for participating in today's lecture. I'll upload this R script for you. And if you don't have any questions, you can leave the meeting. Thank you very much.